addressing is often used with arrays. That is, the address of the array is stored in a register, and the register is then used as the base for indexing. In this snippet, every member of an array is set to 0. The EBX register is used to hold the address. The address of the base array is loaded into the EBX register. Then the size of the array, in this example the array has 5 members, is copied into the ECX register to be used as a loop counter. The instruction that sets the current element to 0 needs to be specified as being 1 byte in length because the assembler has no other way of knowing the size of an array element. The address is then moved to the next member of the array. Because the size of each element is 1, it's only necessary to add 1 to the address. The loop instruction subtracts 1 from the ECX register, and if the result is not 0, it jumps to the top of the loop. Here is the same thing again, but this time it's an array of 5 32-bit integers. The main difference is the way the address is adjusted. In this example, 4 is added to the address each time it needs to be moved to the next element. Here is an example of using indirect addressing. The array of integers is declared as a variable in this C program. Each member of the array is initialized, then it's passed to an assembly language function which multiplies all of its values by 4. The assembly language function uses indirect addressing to address the array. Both the size of the array and the address of the array are passed in as arguments. The size of the array is set up in the ECX register as the loop counter, and the address of the array is stored in the EBX register. The body of the loop is very simple. A member of the array is copied into the EAX register. The register is shifted to the left by 2, which multiplies it by 4. Then the value is stored back into the array. The EBX register is incremented by 4, the size of a 32-bit integer, which moves the indirect address to the next member of the array. Finally, the loop instruction subtracts 1 from the ECX register and loops back to the top if the result of the subtraction was not 0. The C mainline displays the values of the array both before and after the function, so the output looks like this. You can see that the numbers in the second row are the ones from the first row multiplied by 4. Here is another simple example. This is the world's simplest sort routine. It uses the bubble sort algorithm to sort an array of integers. The array is passed in from the C mainline, just as in the previous example, but this array has its values out of order. The algorithm works by comparing each number to the one following it in the array. The last member of the array doesn't have a next one following it, so the comparison counter is reduced by 1 from the size of the array. A member of the array is copied into the EAX register, then it is compared to the next member of the array. If it is less than or equal to, no exchange needs to be made, so there is a jump to the bottom of the loop. If the loop is not finished, the address is incremented to the next member of the loop after the exchange is made, and the loop jumps back then to test the next number. If the values do have to be swapped, the exchange instruction is used to swap the contents of the EAX register with the next member of the array, and the value that was the next member is stored as the current member in the EAX register. At that point, the algorithm jumps back to its beginning. where the address and the count are both reset to their start and the whole process starts over. The array then is finally sorted when the process loops through the entire array without a single swap. Now, this may not be the most efficient way to implement this particular algorithm, but it's got to be about the simplest, and it demonstrates how to access arrays.